Today, he's going to talk to us about Josephson junction-based models of neurons. Professor Bota, please.
Thank you. I hope everyone can hear. Yes, this is something we started quite recently and that I became interested in recently through my collaboration with Professor Kolachi and others at the Institute. So I'm not going to really present detailed results, but rather try to give an overview of the subject as it is today. And I think it's actually it ties in quite nicely with the previous talk, because the advances made in molecular dynamics simulations, I think, would have repercussions on the possibilities of modeling neurons at a more fundamental level as well. So the three parts of the talk will be basically an introduction of the basic model of the Josephson junction neuron, and I'll spend some time explaining a little bit in detail how it works, because that will help to understand the next section, where I will be reviewing the literature that exists. And actually, it's a very small literature, relatively speaking, to other subjects. But nevertheless, there are some fundamental papers that are quite interesting. And lastly, I'll end with a brief discussion of some of the work that we've been doing recently, which is also related quite closely to the neuron, Josephson junction neuron, that I'll be talking about. And I'll explain how that works. So just to remind everyone, the basic parts inside a neuron are very similar to a normal cell, except that the neuron has a bit different shape. It generally has these dendritic parts sticking out of it, and also the axon tail. The thing that is most interesting about the neuron is that it's able to transmit electrical signals. And this happens briefly by the depolarization of the cell membrane. So usually the sodium-potassium pump ensures that there's some equilibrium polarization between the inside and outside of the cell membrane, with the inside being negatively charged relative to the outside. And this is known, if you measure the difference between the inside and outside, that would be what's called the resting potential of the membrane. However, if some stimulus is received, either through the dendritic connections or else from a neighboring neuron by a synaptic connection, then provided a certain threshold is met, there's a channel that will enable sodium ions to flow to the inside of the cell, and that would locally disturb the equilibrium. So there's a depolarization that occurs, and this depolarization, if it is sufficiently large, will then be able to propagate sort of like a wave down the axon, and eventually be transmitted via synapse to some neighboring neuron, or possibly into to activate a muscle or for some purpose. So that's roughly the mechanism that the model has to be able to take into account. And if one looks at the the membrane potential, as the cell receives some stimulus, then when the stimulus is sufficiently strong, it will trigger this depolarization, raising the cell membrane potential. And once that has occurred, there is a negative feedback mechanism that again opens the channels for restoring the cell potential to its usual state of resting potential. In fact, there's a slight overshoot here, which is known as hyperpolarization, when there's a over compensation that happens, but eventually the cell then reaches back to its resting potential. And this signal will then, as I said, be transmitted along the axon. So basically a very simplistic overview of that is shown in the bottom corner here, where you see the depolarization in the membrane traveling down the axon. Now that I explained a bit about the neuron, let me now explain a little bit about the Josephson junction. The Josephson junction was postulated by Josephson in 1962 already. He had the idea, or he worked out, that if you place two superconductors next to each other, there's a possibility that current can flow across the gap, even for zero applied voltage. So in other words, due to the tunneling of the Cooper pairs within the two superconducting materials, they're able to cross the gap unimpeded, provided certain conditions are met. And Josephson worked out the relation between the macroscopic phases of the wave functions on either side. And he worked out the current in terms of the macroscopic phase is given by this sinusoidal relation. And he also worked out the voltage relation between the phase and the voltage. So that was his key contribution. And this effect was then later observed in about a year later by his supervisor, I believe, Anderson, and co-workers. And of course, everybody, well, most people know that he won the Nobel Prize for this discovery. This is an ideal situation. In a real situation, the junction is normally connected by some leads and some contacts that cause additional capacitance and resistance in the model. And so usually one of the models used includes this capacitance and resistance. So you have an ideal junction, but also one has to take into account resistance and capacitance that occur in non-ideal behavior. And this leads to what is now known as the resistively and capacitively shunted junction model of the Josephson junction, which is a very widely used model, phenomenological model of such a junction. So in this model, basically the current passing through the junction consists of, on the total current flowing through here, would consist of a diffusion current, which is modeled by the capacitor, and then a purely ohmic part, which is given by the second term, and then the Josephson current itself. And the voltage is just given by the usual Josephson junction relation. And one can then see also first of all, one can rewrite these in a more convenient form. Usually it's written in some dimensionless units, and they look something like this. So there's the voltage phase relation, and then the current through the junction and the sinusoidal term. And this is basically the resistor causes some sort of a damping effect. So this term, this term at the bottom is the damping in the system given by gamma. The junction then can be seen to exhibit a type of hysteresis loop. That is, if you start increasing the bias current from zero, increasing the current upwards, at first there is ideal superconductivity. In other words, the current increases without any increase in voltage across the junction. That is until you reach this critical current, which in these units have been normalized to 1. At the critical current, the junction then jumps to a resistive state. And for higher currents, if you go further up than the critical current, it behaves like a ordinary ohmic device. In other words, V is proportional to I. Coming down again, however, the junction will remain in the resistive state even when you drop below the critical current until you eventually get to a stage where it stops, where the phasors stop rotating and the junction then falls back into the superconducting state. So this is a typical basic behavior of the junction, which is needed in order to understand the behavior of the neuron, which I'll explain next. Now, the circuit that we use to describe the model of a neuron looks something like this. It consists of two junctions, and each junction here, in the red circle, is actually a RCSJ junction. So it includes some resistance and capacitance, as I explained previously. But in addition to that, there are, in this case, two bias currents that are supplied and two inductors. There's what's called a pulse junction and a control junction, and similarly the pulse inductor here. What happens basically is in order to mimic the behavior of the action potential that we saw previously, one would set the bias current at a value where this pulse junction is almost at the critical current. So it's about to start entering the resistive state. And then, depending on the input current, if the input current so the bias current is fixed, but if an input signal is received, this is the type of signal that would be received from, say, a synapse or something, then it can increase the current through the pulse junction and cause it to start developing a voltage. As soon as the pulse junction develops a voltage, however, it reduces the current flowing through this branch and increases the bias current flowing through this branch, which then has the effect of stopping the junction or slowing down the pulse junction, with the effect of causing the control junction to rotate in the other direction. So this circuit is then, in this way, able to mimic the same behavior that we see in the action potential. And the equations for it are quite simple. They are basically you'll recognize the equations for the junction. Again, this is the damping term, the sinusoidal term. And then these are the bias currents that are passing through the junction as we had before for the single junction. They're a little bit more complicated now because the currents will branch at each of these junctions. So this is taken into account by these factors here. But then there is an additional term which couples the two junctions together as a result of the inductive coupling, and that's given by this lambda factor. So the inductances couple the two junctions together by this quantity which we call the flux. And when one does a simulation of the system, what one then finds is that the flux behaves very much like the action potential. So here in this diagram at these parameters is a short simulation of the system, starting with where the input signal, the I in that we saw previously, is systematically increased. And you see that at first not much happens, but when it reaches above about or at 0.2, there is sufficient input current to trigger this response that I've just described. And so one gets these pulses in the flux. In Josephson terms, it's called a single flux behavior. So that's the basic operation of how the neuron works. Now, so just to recap things again, the flux in the system that we have, or in the model, corresponds to this membrane potential of the neuron, and the pulse voltages and the control voltages are basically equivalent to the sodium and potassium currents that would flow in and out of the cell. And then I in would be some sort of a synapse current or whatever the integrated signal is that the cell receives. Because the cell also takes into account multiple inputs, and it will effectively integrate the inputs to reach a state where it either fires or doesn't fire. So it's not as straightforward as having a single input in the case of a real neuron. Now, the junction model that I've described has some very attractive key features that have been mentioned in the literature. One of them, as I've already mentioned, is that the action potentials only occur when the input is above a certain threshold. The second one is that the action potential that the junction provides actually matches very closely that of another model, which is considered to be one of the best models around. And thirdly, there are, depending on the damping, the neuron can behave like a Hodgkin class 2 or class 1 neuron. And fourthly, the action potential can, there is a refractory period during which the action potential cannot be reactivated. So I'll briefly look at these 4 points just to make it a bit clearer. So here is a simulation of the equations we saw previously for a single neuron. And in the first instance, the input signal is given by this black dashed line. And here the input signal is set at about 0.2, but as you can see, it's not sufficient to trigger the behavior that we want. In other words, the neuron is not firing, it's below threshold. But if you just raise the amplitude of the input by a small amount, in this case to 0.2, I think it's 0.22 or something like that, then suddenly the neuron starts firing. This is a very important property and a very beneficial property of the model. The second key feature that I describe is the comparison between the action potential provided by the Josephson junction and the Hodgkin-Huxley model. And this comparison has been made in the literature before, merely basically what it amounts to is a similarity in the shape of the potentials that are provided by the two models. Then thirdly, as I said, there are two classes of Hodgkin neurons that were described originally. In class 1 neuron, the frequency increases with input strength, whereas in a class 2 neuron, the frequency is more or less independent of the input strength. So in the top figure here, one can see when the damping is above 1 in these units, then increasing the input current effectively increases the frequency of the firing. You can see clearly here these peaks are widely spaced at the beginning, but they become closer and closer as the input signal is increased. Whereas if gamma is below the threshold value of 1, then more or less independently of the input strength of the current, the firing occurs at the same frequency. So there's another feature that is in accordance with what is observed in neurons. And lastly, the idea of the refractory period, which is also known, is demonstrated here in the simulation. In the first simulation, we have two pulses, input pulses, that both trigger the action potential. But if the same amplitude and width pulses are positioned close together, in other words, they're two signals following each other very closely, it doesn't trigger the action potential a second time, because the second input pulse falls then within the refractory period of the neuron. So these four features really make Josephson junctions a very attractive model for using in neurological models. Briefly now, I come to the related literature. And before I do that, I just would like to give a historical timeline of how things roughly developed. So in 1952, Hodgkin and Huxley described their model of the neuron in a very famous paper. 1962, as I mentioned, was when Josephson described his effect for the first time. And after the description of, or after the invention of the Josephson junction, ideas started developing of using the junctions as a basis for some sort of neurological model. However, in the literature, one finds very little is mentioned of such proposals, and the papers that were written don't seem to be cited more than once or twice. So I'm not really sure why that is. But the real work on this junction seems to have begun in 2010 with the group of Chegal, who wrote a paper in Physical Review E. And in that paper, they developed this circuit, which I've just explained, based on existing technology that already existed for squids, basically, where they have a rapid single flux quantum device. So they developed a circuit which is quite similar to what was used before, and the motivation for their work was based on the idea that using Josephson junctions, one would be able to simulate much larger numbers of neurons. Now, based on the previous talk we saw, that might seem like an unnecessary step, given that computational power has evolved so rapidly. But nevertheless, one has to remember that in a typical neuronal system, there might be hundreds of thousands of these neurons. And even though we can do molecular dynamic simulations with perhaps millions of atoms, it's not really feasible to solve systems of dynamical equations that contain more than maybe 10,000 equations at once. It's just not possible, at least not as far as I know. So the idea with the Josephson junctions was that this could provide a real experimental way of manufacturing a analog system that would simulate a real network of neurons. Of course, there were drawbacks. The main drawback to this proposal is the fact that Josephson junctions have to operate at cryogenic temperatures, and that generally raises the cost of doing such experiments. And perhaps for this reason, there wasn't much uptake for the idea, and still hasn't been really taken forward in terms of experimental work. Nevertheless, this paper has been cited 72 times, and it is quite an important paper in its field. And here I just show also, in addition to the basic neuron, these authors show also how to connect the neuron to a chemical synapse. So this capacity here is modeling the synaptic connection, which may be to another neuron or to something else. And in their paper, I think they performed only simulations of, I think, only 1 or 2 neurons at a time. So they didn't really explore the large numbers of neurons, even though the proposal of the paper is based on that idea of generalizing a system to really large numbers, like hundreds of thousands. And then later, in a follow-up paper, they investigated what would happen if one coupled more neurons together. So the same group then followed up with this paper in 2014, where they studied the synchronization effects between neurons that were coupled together. And again, they only considered 2 neurons in this particular paper, but all of it was through simulations. And they found that basically the neurons synchronize out of phase when the coupling is weak and in phase when the coupling is strong. So that was the main finding of this work. Unfortunately, I think the authors were at you can see they were at the Colgate University in New York, which is probably not well known for its physics department. I think it's more of a liberal arts college. And I think it must have been very hard for them to find, experimental collaborators at that stage, because in 2017, the same group finally managed to perform an experiment with the help of a consultant. You can see they consulted somebody in Colorado, and this is one of these labs that make Josephson junction circuits, and they were able to fabricate and test 2 junctions, a circuit for 2 junctions that basically, that, like you saw in the previous paper. And they actually performed experiments and observed the flip bifurcation that they mentioned in the previous paper experimentally. And thereby they provided at least a proof of concept of their proposal for the Josephson junction neuron, an actual working experimental system. Of course, it's still a long way from 100,000 neurons, but it's a proof of concept nonetheless. Also in the literature, one finds other neuronal models based on the Josephson junction. In 2015, a group from India in collaboration with Israel wrote this paper about bursting dynamics in a population of oscillatory and excitable Josephson junctions. So here again we see the basic equation for the junction on the left with the bias current, but the junctions here are coupled by some linear coupling, and the coupling occurs in terms of the phase derivative. So basically it's a voltage, these are voltages across the junctions. Now, with this coupling, the group was able to show that very similar bursting behavior occurs just in the ordinary junctions coupled together in this way. So the junctions basically separate out into two groups, and each group displays separate bursting behavior, which is similar to the action potential that we saw previously. So there are various ways of using the Josephson junction to model these effects. And unfortunately, what this model lacks is the ability, unlike the previous model that had definite proposal for implementing the system, this model seems to be purely mathematical because it is not clear how one would actually construct a system that is coupled in this way. So the coupling here is purely mathematical, and the study is also purely in terms of the mathematical and numerical results. So not much citations for this paper, unfortunately. Then recently, one will also find a review of the idea of using Josephson junctions for modeling spiking and bursting in neurons. And in this paper by Mishra, which was written last year, they investigate a simple RCSJ junction shunted by a resistor and inductor. And again, this system is capable of displaying similar behavior to what we desire for modeling the neuron, and hence the interest in it. The equations again are fairly recognizable. One again has the voltage phase relation of Josephson, and then the junction equation looks like this. This is the damping term, the capacitive term, and this is the damping term, but the damping now depends on the voltage. And then the sinusoidal term and the usual bias current. So it's a relatively simple model, actually a very simple model, and yet it exhibits some of the desired properties that are needed for modeling the neuron. Now, lastly, I will discuss some of our related work. We started off in 2020 with a model related to the famous Kurumoto model that was aimed at modeling memory. And then recently we've also extended this work to study chimera patterns of synchrony that occur in the same model. The idea here is based on the relation that exists between the Kurumoto model and the Josephson junction. Actually, whenever one has any limit cycle type of behavior, when there's some periodic behavior or a limit cycle behavior, one can associate a phase with such behavior. So regardless of the nature of the signal, whether it's this one or this one can define a phase of the signal. And every time the signal repeats, the phase will effectively repeat, just like a pendulum maybe going round and round. So the idea with the Kurumoto model is it comes from phase reduction theory, and it represents a very general situation of some limit cycle system that exhibits limit cycles that is coupled together. And the so the Kurumoto model is really a generalization of any coupled system of limit cycle oscillators. And the coupling turns out to be of this form. In terms of the phases, it basically works out to be the sinusoid of the difference in the phases. And this then is the coupling strength, how strongly the phase I is coupled to J. And then I'll talk about this last parameter in a minute. But in the model that we investigated in our previous work, we make use of this Kurumoto-Sakaguchi model to model the neuron, together with the Hebb rule for synaptic plasticity. The second, the second part of the equation governing the strength of the coupling is basically modeling the connection between two neurons. And the idea is that the strength of the connections between the neurons are actually responsible for memory in the system. So the Hebb rule states essentially that the synapse is strengthened if the presynaptic neuron excites the postsynaptic neuron, and otherwise, if it's the opposite way around, it's weakened. So if the phase I and J, the difference here between I and J is leading, then it uses one of these equations, which then increases the value of Cij up to a threshold of alpha. Or if it's the other way around, then the strength will decrease. So in that way, the strength of the coupling between the neurons can be either increased or decreased. They can dynamically evolve according to what the system is doing. The typical coupling matrix here would be like the one shown in the bottom here, where the coupling doesn't extend globally, but is some sort of a local coupling. So in other words, the black here represents values of Cij equal to 0, so there's no coupling. But if you look at a particular value of J, it's only coupled to its nearest n neighbors, little n here being the number of neighbors that any particular neuron is coupled to. So that's the basic idea. And in our work, the model as it stands here already existed. But what we did is we also investigated the effect of adding this frustration parameter in the system. Now, the idea of frustration is basically related, or comes from a magnetic system originally, where you might have a system where there's both ferromagnetic and antiferromagnetic coupling present, and the one tends to align spins, the other one tends to make them point in the opposite direction. So there's a competition between coupling that wants to align everything and coupling that wants to anti-align the spins. And this is what's known as frustration, because in the end, the system has to reach a state where of minimum energy, let's say, and it may not be a fully aligned or fully anti-aligned state. It might be something in between. In the case of the model that we use here, the frustration can be thought of as playing a similar role to what I said earlier, where let's say a neuron might receive multiple signals from adjacent synapses, but in order to decide whether to fire or not, it has to reach some sort of a integrated combination of whatever the signals are that it receives. So this parameter of frustration plays a role much to that effect. And what we did is we investigated how the addition of this frustration in the system can affect the synchronization of the system of neurons. And more recently, in the paper that we just communicated in Frontiers, we investigated how that the addition of frustration in the system can make possible these chimera patterns where some of the neurons are synchronized, where one group of neurons are synchronized, but another group are desynchronized. So this is the two main contributions that we've made more recently. And hopefully in the future we'll be able to extend this work to either investigate Josephson junction neurons more directly, or else via this abstraction of the Kuromoto model. We're hoping to extend our work in that direction. But I hope I've provided at least some overview or flavor of what the work entails. And I also include here a bibliography of all the references that I used or consulted in order to prepare this talk. So if anybody is interested, they can all be found at the end of this talk. Thank you very much.
Thank you, Professor Bota. And if anyone has any questions, please. No questions? So let me ask a question. How about the number of junctions or the number of neurons that can be simulated? It is related to your last question, to the question that you put to the previous speaker.
Yes. Realistically, when one has a system of of coupled ordinary differential equations, realistically, I think about even 1,000 or 2,000 becomes quite difficult, because there is no real way of parallelizing the integration schemes for such a system. So it really is limited in terms of performing dynamical simulations on such a system. So, yeah, so it's a long way off from 100,000 or even a billion neurons that one would ideally like to simulate. But perhaps there may, well, of course, the introduction of the Josephson junction doesn't help for numerical simulations. The idea behind it is that it will enable experimental manufacturing of a system, which can then be used as a simulation tool. Yeah. We seem to have lost Professor Kulachi. I think I will.
Oh, okay. Can you hear me?
Back.
Hello?
Hello? Yes.
Can you? Hello?
Please.
Okay, can you hear my voice?
I can hear you, but how about everybody else?
Okay, great. So I'm just gonna blurt out my question, and if the speaker can hear it, maybe they can answer the question.
Yes, I can hear.
Okay, good. Can anyone? I think you should be. You should be on, I think, but.
Okay, I keep getting on and off, but I'm gonna try it one last time, and if this gets through, it's great. So I was gonna ask you about the frustration effect. It kind of reminded me of introducing a delay for communication between neurons. So in a sense, that is kind of setting them to synchronize in such a way that they wouldn't exactly spike at the same time. I don't know whether I'm communicating or not. If I forget what was it, sigma? The parameter was sigma. If sigma is 0, then they're synchronized. They tend to be synchronized in the sense that they would fire at the same time. If you introduce some sort of phase between them, then you're saying that they would synchronize not exactly at the same phase, but with a bit of a difference, which to me translates to having some sort of time delay for sending a signal from one neuron to the next neuron.
Correct. Yes, correct.
Is that okay? So have you considered considering the sigma as an array instead of a fixed parameter? In other words, sigma ij instead of sigma for all coupled neurons, having some sort of randomness introduced into the problem. Let me just ask one last question too, so maybe you can answer both of them at the same time. I didn't understand what your starting network was. So if you're looking at all-to-all network, or do you have some sort of structure for your adjacency matrix, CIJ? Thank you.
Yes. Okay. So to answer the last question first, in this particular model I was talking about, we dealing with a cyclic type of model or a circular type of topology where there's effectively a periodic boundary condition, so the cycle starts to repeat in this particular situation. You can see that from the form of the adjacency matrix. To answer the other question, no, we haven't considered sigma as a matrix. In other words, having different sigmas for each phase difference. That has been done in other connotations, I think, because some of the other work we do, or I do, is related to power grid modeling. And in that context, I think there have been papers that have considered that sort of model. But in our work as such, we have not yet done so. And it is perhaps something to consider for future work.
Okay, thank you. Did I understand correctly that your network did not have any small world effects, so each neuron was only coupled to its immediate surrounding?
Yes, the neurons are coupled
Okay.
to their nearest n neighbors, so they can only interact with the neighbors that are within a distance of small n from each neuron. So, and they are, so the strength of the coupling may differ, but essentially they only interact with the n nearest neighbors. And then the topology as a whole is a cyclic one, so that if you get to the nth neuron, you again start back at number 1. It just keeps repeating in this.
Okay, and what's the range of the interaction? Like how many, what percentage?
Well, in this work, we're able to simulate a couple of hundred neurons at most, because of the nature of the equations, and the range of interaction may be, well, anything from nearest neighbor to anything less than n, basically. But typically we would use, let's say, 100 neurons with an interaction range of maybe 40 or 50 or something like that. Now you can see an example here at the bottom. For example, this is a 60 neuron model, and the interaction is maybe ranging for 20. So from 40 to 60, there's interaction out of the total of 60. Yeah.
Thank you very much.
Okay.
Any other questions? Okay, so let me thank you again, Professor Bota.
All right, thank you.
Bye.